Hello. This will be a demonstration of Proposition 3 from Book 9 of Euclid's Elements, which says that the square of a cube number is also a cube number. We're, of course, given a cube number a. We're also going to square that cube number, call that the number b. So a times a makes b. And what we want to prove is that the number b is not only a square number, but that it is also a cube number. We're going to begin by taking the number c, such that c cubed makes a. The way that Euclid puts this is that the number c is the side of a, because if we represent a as a cube, the side lengths will be c long. So c cubed will make a. Furthermore, we're also going to take the square on c itself, call that d. So c times c makes d. And because c times c has made the number d, the unit measures the number c the same number of times that the number c itself measures the number d. That follows simply from the definition of multiplication, definition 7:15. And because the unit measures c the same number of times that c measures d, we can then turn this into a proportion by definition 720 and say that the unit is to c just as c is to d. Next, we recognize that the number c has been multiplied by two numbers to make two products. C times c has made d, and c times d has made a. C times d making a is just obvious because the number d is equal to c squared. So c times c squared, which is the same as c times c times c, which is the same as just c cubed, that obviously makes the number a. We had made the number c in that way in our first step. So c times c makes d, and c times d has made a, which then means by proposition 717 that c is to d just as d is to a. Because we know when a number multiplied by two numbers makes two products, the two numbers multiplied are to each other as the products, so that because c multiplied by c and d, making d and a respectively, c is to d just as d is to a. But we also know that the unit is to c just as c is to d. So we can put these three ratios in a continued proportion made up of the unit, c, d, and a, because e is to c just as c is to d, just as d is to a. Now next, we know that a squared makes b. We were given that. And so again, by the definition of multiplication, definition 715, the unit measures a the same number of times that a measures b. And just like last time, we can convert this into a proportion by definition 720 to say that the unit is to a just as a is to b. But we know that between the unit and a, there are two mean proportionals, namely c and d. We had arrived at that in our previous step, step 3. So that because there are two mean proportionals between e and a, it then follows from proposition 8:8 that there are also two mean proportionals between a and b. But we know that a is a cube number, and we know from proposition 8:23 that if four numbers are continually proportional, or in other words, that there are two mean proportionals between two numbers, and the first number is a cube number, the fourth number will also be a cube number. That's what proposition 8:23 tells us. So that because there are two mean proportionals between a and b, and a is a cube number, b is therefore also a cube number, which is what we set out to prove, which means we're done with the proposition, therefore, etc., q, e, d. What this is going to look like, just with a particular example, is that 8 is a cube number. It is equal to 2 cubed. And so what this proposition then tells us is that if we take the square of 8 squared, that makes 64. What this tells us is that 64 is itself also a cube number. Namely, it is equal to the cube of 4. 4 cubed makes 64. So you see that this proposition holds. One final mark to make about this proposition is that this sort of logic might seem obvious to us who are used to these exponent rules. We know that if a is raised to some power b, and that whole thing is raised to some power c, we know that this is the same as taking a to the power c and raising that whole thing to the power of b. Or in other words, that the order of exponents is interchangeable. It is commutative. So it seems fairly obvious that the square of a cube number would also be a cube number, because this is the same as taking 2 cubed, raising this whole thing to a 2, which is the same as taking 2 squared and then raising that whole thing to a cube. So you might be wondering, why go through this whole logic if we can just arrive at this proposition simply by the rule of exponents? Well, the reason we go through this proposition is because proving this rule about exponents is hard. Most people just take it as given. I took it as given for a long time, but it's kind of a hard thing to prove. And so that might make you ask, well, how do we prove that this is true? And you would prove it in this way. This is the simplest form of this rule, where B and C are 3 and 2 respectively. But you can use the same logic outlined in this proposition 9.3 to arrive at the general case where B and C are any number. So even though this might seem trivial to us who are so used to this exponent rule, this exponent rule actually comes out of this proposition. So that's why we do it. That being said, I'll end the video here and move on to proposition 9.4.